Anshika, we are live.
Okay, ma'am.
Yeah. Namaskar, everyone. This is Malika Pathak from Miranda House. Greetings on the occasion of Basant Panchami. May the spring season bring sunshine, warmth, good health, and happiness to all of you. So, on the behalf of Miranda House and Ramanujan College, I welcome you all to the day 5, a very, very special day. It is the day of Basant Panchami of the Faculty Development Program in Chemical Sciences. We welcome our keynote speaker, Professor Akhilesh Kumar Verma. Professor Verma received his PhD degree from the Department of Chemistry, University of Delhi. He has joined Dr. B.R. Ambedkar Center for Biomedical Research, University of Delhi in 1998, and he has been serving there for past so many years. He has also served at the School of Physical Sciences, JNU, for nearly a year in 2015. He did his postdoctoral research work from 2001 to 2002 with Professor Alan R. Kartritsky at University of Florida, USA. And he has also worked as visiting scientist from 28th June 2007 to 31st August 2008 at Iowa State University of Science and Technology, Ames, Iowa, USA, in the laboratory of Professor Richard C. LaRocque. Professor Verma has guided 32 PhD students and has published more than 132 research papers in international journals. His research interests include copper, palladium, catalyzed coupling reactions, synthesized methodologies and design of small organic molecules using alkynes chemistry. Professor Verma has been elected as the Fellow of Indian National Science Academy. He has been awarded CRSI Bronze Medal and became a Fellow of the Royal Society of Chemistry, London. He has been awarded UGC Mid-Career Award in the year 2017, is also the Senior Fellow of the Institution of Eminence, University of Delhi. And now I kindly request Professor Verma to enlighten us with his talk. Sir, the room is all yours. Welcome, sir.
Thank you, Dr. Malika, for your very kind introduction. And first of all, I would like to apologize because my throat is not perfectly right. So my voice not be as usual, as I think Anshika knows me very well. So, it's always a pleasure to give a lecture and to share what we can do for our university and the teachers of this country. So if you can see, the title of today's faculty development program is Smart Designing of Organic Molecules and how to publish research finding in a reputed journal. Right. So we all are colleagues. I know we all are teachers. So in the beginning, I would like to say one thing. Once we are a teacher, the first and most important responsibility of a teacher is to serve his and her country. Whatever will deliver, whatever we will give, that will add to the value of our country. And in what way we are contributing, that's, is one of the best and noble profession, that is a teaching. We nurture the students, right? And for a teacher, the most important thing is there is no end of learning. There is always scope to learn. And similarly, when I started until date, still when I go for any lecture or I look some book or when I visit some library, there is always scope for learning. So one should not think like he's a master or he knows everything. Once, like one person think like that, he's a master and he knows everything, then he and she cannot progress. The progress will stop. It's always is a learning process for all of us. Right? So, and all of you are teachers. Some people might be working in some good college and some might be in some state college. Some might be in some different college. Doesn't matter. The first important thing, we are teacher. And everybody is having the same responsibility towards the students in the country. And when I joined Delhi University, when I started a research career along with the teaching, there was nothing. One need to make an efforts to get the things done. When you start your research career in the beginning, always challenge will be there, and tough challenge. And once you cross the first challenge, establishing and publishing your own paper is one of the great challenge. That should be your design and your own paper. So that is why I choose this topic, because several people, several scientists and teachers, sometimes they perform the experiment, they have a good result, but they are unable to publish in the desired and well-reputed journal, or one can say high impact journal. That is always tough task, but one need to have a proper approach. So that I will discuss after coming to the second part of this talk, that is how to publish your research finding. So research is always depend upon your basics. Your basics and how you can utilize your basic knowledge of your chemistry. I was like same like you people when I started my career, and maybe worst, because I did my MSc from a very small place that is called Bipin Bihari College, Jhansi. Then I moved to IICT, where I learned some chemistry. I was enthusiastic to learn the chemistry. I was staying up to late night. When I returned back to Delhi University and joined in 1998, there was no NMR facility. There was only one NMR with Professor Parmar in the Department of Chemistry, and they used to allow only one NMR sample in a week. Can you imagine with that? One sample in a week, you can publish a paper? No. But I did not give up. I looked for another route, right? So another, like, pay and get it done. So IIT Delhi facility was there, NMR facility and mass facility. So I used IIT Delhi facilities. And 3 and 4 times in a week, I used to go along with my sample. And one day I gave, and next day, or maybe next to next day, I used to pick up the spectra. So what I mean to say, when you need to start your career, when you need to establish your lab, in the first few years are very challenging. You need to give everything. And once you establish your paper, publishing your paper will become easier. Right? So now you can see how I started my career and how I reached from that place to this today where I am. So now you can look here, the start of journey. So when I did postdoc with Ketresky, I learned this benzotriazole chemistry. And now you can look here. It is a very simple chemistry. You can look here what we have used. We have used this amine, right? And aldehyde and benzotriazole and Lewis acid. So what happens? They forms imine. They generate imine. And if you remember the basic chemistry, indole and pyrrole, they are electron rich in nature at 2 position when 3 position is blocked. And the close proximity is also very, very important for making the bond. So this is what I have designed. Look here. So this you can get easily once you have any X here in nitro, that nitro later on you can reduce. So you can get easily this starting substrate. And with aldehyde, benzotriazole help for generating iminium. So this imine with AlCl3, you can get this imine, right? And imine, and then the 2 position of indole, which is electron rich in nature, attacks on imine. So you can get, so this we got selectively. And this the chemistry we use in the beginning. And you can see here, these all wide variety of molecules and these publications we made in the beginning. But always remember, postdoc work you cannot carry for a long time, right? Because once you are establishing a lab, they will say you are continuing your postdoc work or PhD work, right? And then what I could find something new. This benzotriazole, you can look here, benzotriazole, hydroxybenzotriazole, bisbenzotriazole, and tridyl benzotriazole. We have found new application of this. That is, we use this benzotriazole as a ligand for 7 coupling reactions. Suzuki, Heck, oxidative Heck, Sonegasha coupling, CN coupling, CS coupling, and intramolecular CC bond. So this is what we come to know something new. We got a ligand which nobody knows. And it was one of the cheapest ligand because benzotriazole is very cheap and thermally stable. One can keep for years and years. So one should design the chemistry in such a way so that can be sustainable, cost effective, and robust. So this is what we come to know, that we have published these 3-4 papers using this ligand. And now look here, how smartly I have designed the next chemistry. So in lab, if you look, we are using these 2 building blocks. Orthoalkyne and aldehyde, ortho-halo-aryl alkynes, and that can be easily constructed from respective halides by Sonegasha coupling reaction, which is well known. So first is what something new we gave to this globe, that is hydroelimination of alkyne. So in this area, we have published, since 2009 onwards, we have published at least 25 to 30 papers in hydroelimination field. So what is this chemistry? If you look this chemistry, this is what is a hydroxy methyl benzotriazole we have used as a ligand, right? I will show you how we have designed this thing. And all these useful molecules, you can see these all, these are present in the natural product. And this last one is used as this transistors, organic materials, right? More important is how we can design and how we come to this. Look here. This is a well-known chemistry of annihilation of any N-heterocycle. When you take any N-heterocycle and aryl halide with copper and palladium, you can do CN bond coupling. That is also known as Buckwald-Hardwick coupling. It was well known. And another is this electrophilic cyclization. It was well established by Yamamoto and Laroque. So if you have, look here, this X, right? In X, once you have a lone pair, and once you can activate this alkyne, and alkyne can be activated easily by a metal or by an electrophile, right? So, and this can easily cyclize, and you can get a cyclized ring, 5-member or 6-member, where X may be sulfur, selenium, oxygen, nitrogen, right? So, combining these two chemistry, this chemistry and this chemistry. Now look, what we were going through, what we have published earlier. So based on that, what we have designed, like, look here. So this is indole or maybe any heterocycle, ortho alkynyl halide. So what we thought, what the ligand which we have developed for CN coupling reaction will help in generating this CN coupling, right? And we will get first this, and in situ, this alkyne will be activated by a metal, that is copper, and the C2 position will attack here, and we will get indolo 1,2A quinoline, which is a very, very useful molecule. So this is what we have designed, and we perform the reaction. You can look here. We perform the reaction of 3-methyl indole with this bromoalkyne using 5 mole % copper iodide. Potassium tertiary is always used when you have to do the CN coupling. In the ligand, L2 is hydroxybenzothiazole that is required to make a in between the intermediate that helps in the coupling reaction. So this is what we perform. 110 degree. Several experiments we have performed, and what we got is 3A. But remember, the complete and proper characterization of your compound is very, very essential. There was some possibility of this which we came to know later on, right? So actually, you know, the proton spectra, if you look these two, right? Same number of carbons, same number of hydrogens, same mass. How to say whether we have a this or this? It was challenging. My manuscript was ready to submit in organic letter. Then in between, I thought, to give more support, let's look the crystal structure. When we look the crystal structure, you look this one, it didn't say we got this one. It says we got its regioisomer. Then pyrrole series, we develop another series of compound that is a pyrrole. And here also, it gave the same result. What we expected, we didn't get. We got its a regioisomer. And whenever you get something different which you did not expect, and when you completely characterize that product, and when you know how this product is forming, that is how you will get something in new chemistry. So then this crystal structure rule out, this is what we propose, right? This is what we propose, this one, and to get this one. But this is ruled out. Because crystal doesn't say we got this one. Then this is what the product we got. So we thought, because there is some reports where the C2 annihilation is also known, right? So we thought maybe the reaction is proceeding via first C2 annihilation like this, and then intramolecular this cyclization, and which is giving this, right? So and when you design any chemistry, you need to give a proof for your chemistry, right? So to prove this second proposed route, we perform a first control experiment. So indole and 4-bromoanisole using a same standardized reaction condition, we perform the reaction. But it was surprising. We got only CN-related product. Indole and pyrrole, both we got the same. And we did not observe any C2 related product this at C2 position. At C2 position. That was not observed. So this experiment again says the reaction doesn't go via formation of a C2 annihilation. So then only one possibility was left. That's called inception of route C. That is simply via hydroamination. Right. So what is that? Now look here. This is very, very important. This opens a new chemistry in presence of halide and all, whatever you have a catalyst and all. That does not give a CN bond. That means CN annihilation doesn't take place. It gives the hydroamination, means attack of NH on alkyne. So that is called a preferential hydroamination or regio and chemoselective reaction. So that after ruling out first these two possibilities, we left only with third option, that is called hydroamination. So hydroamination and followed by the ring closure between this and this. So you can see here. This is hydroamination. Then bromo here you have. So that will give you a first is intermolecular hydroamination and second is intramolecular C2 annihilation. Right? To confirm this, we perform again control experiment. We need to confirm this. So we look the whole literature and I could find only one example of hydroamination, that is by Yoshinari Kondo, right? So for this, look here. We perform a reaction of indole with diphenylacetylene simply. But what we can see, we got a hydroaminated product. That supports the reaction proceed via first hydroamination, means this attack on this. Without any halide, we perform the reaction and this clearly indicates the formation of this product clearly indicates the reaction hydroamination takes place. And then we look the literature and we could find only one example, addition of pyrrole on this by phosphazine superbase 24-hour 120 degrees centigrade. This is phosphazine superbase that was published in 2004 by Yoshinari Kondo. So this also supports like hydroamination is possible in presence of base, but what they use is phosphazine superbase, and only one example was there because this study was something different. But we got some support from this, right? Then we propose this mechanism. Now I'll not discuss this mechanism. It's very I don't think it will take much time. Now look here. So after this mechanism, we published this paper in Environmental Chemistry in 2009. And this whole work I did with my own hand. Some part was done in India, and some part I did when I was visiting scientists in Iowa. And I can remember still how many columns I have done for this work. So that I will not discuss here because we don't have time. Now, after that work, we continued this work and to support the mechanism, because that was proposed mechanism we did not confirm. So simply we perform the reaction of N-heterocycle with terminal and internal alkyne. And now here we did not use any copper, only KOH and DMSO. We could observe the formation of E and Z that depend upon time, right? So that clearly indicates the hydroamination can take place easily simply with KOH and DMSO. DMSO is used as a high boiling solvent. Later on, I will tell you what is the role also. So now this is a crystal which clearly says, so this with the control of the temperature and time, E and Z both can be selectively observed, right? So this is what we published 2 papers. One is organic letter, one is in JOC. That is full length of paper. Organic letter means communication, that is novel finding. Then full paper we publish in JOC. And then further, to support mechanism, because that was proposed. And once you have something new, you can always continue that work when you have something new. So what we have confirmed late in this experiment, regioselective preferential nucleophilic addition of N-heterocycle onto Hydroelimining means, even though if you don't have a halo at 2 position, if you have a halo 2 position, you will get cyclized product. But the thing is that if halo is at 4th position, it will remain up to hydrominated product. And we did not get any CN annihilation product when we use alkyne with a TMS, because TMS can be kicked out during the reaction when you are using base. So that means it is terminal alkyne, right? And this we further confirm by crystal. You can see here, halo is intact and you got a hydroaminated product. So this is another organic letter we published to confirm it is a preferential nucleophilic addition of alkyne and heterocycle onto alkyne rather than CN coupling, right? So then we confirm the proposed mechanism of 2009 paper in 2012. What we have confirmed, what we have proposed, there are 2 routes in the 2009. First is the oxidative addition right here, and then hydroamination. There in that mechanism we propose 2 routes. But with these experiments, what we come to know, first is a hydroamination, and then this is a ring closer oxidative addition, and that gives this product. So this is how you can see we started the chemistry in 2009, and then finally with several experiments we confirmed the proposed mechanism in 2012, right? So and then we extended the same chemistry by putting the nitrogen here, and several naphthyridines we have prepared, and further we extended with the bis alkyne dibromo, and by using, now you can see here, these compounds which are used for electronics, transistors, can be synthesized by using this chemistry. So we have extended the application of that chemistry. Now coming back to what we have initially designed. Initially what we have designed this, but the proposed route we did not get this one. So we changed this one. So we thought maybe first we prepare this compound and then we'll put the Sonogashia coupling reaction. We'll get this. So now once we have alkyne of this, the 2 position, so this alkyne with iodine can be activated, right? And this will attack here. And this is what you can see here, the mechanism. Once you have alkyne, you will get a iodinium intermediate, C2 position being a electron rich in nature that function as a nucleophile, will attack on this close proximity cyclic intermediate. And once it will attack here, this will open and you will get this. And with the release of this proton, in proton will be Hi. So this, you will get this. And in this, all these reaction, you can see here, sodium bicarbonate is used. Why sodium bicarbonate is used? Because iodine is there and H positive is there, they form Hi. Solution become highly acidic. To neutralize that solution, because once you have very highly acidic solution, that will decompose your compound. To neutralize this, sodium bicarbonate is used. That will neutralize the Hi which is formed in excess. So this is further confirmed by the crystal structure, which was in agreement what we got it. And now look here, once you have any halo group, right? Halo group can be easily substituted by a various coupling reaction. This is what most of the industries are doing. So then we did Suzuki. You can put this any kind of thing, and the Heck coupling and alkyne annihilation, you can prepare such kind of compound. And then CN coupling, you can put any N-heterocycle. So this is what we have shown. Once you have an iodo handle in your molecule, this can be further utilized for making a library of compound. Right? And now, the more important is when you look these two, right? This is what we made through just by iodocyclization and then Suzuki. And this is a product we made through the hydroemination. These two are regioisomers. But when you look this methyl group, this methyl and this methyl, if you can look here, this methyl is 1.98 because of the anisotropic effect of this phenyl ring, which is close to that. And this is far away from this. There is no anisotropic effect. So this is, you can see here, is 2.88. So this is 1.98. This is 2.88. Right. So both are regioisomes, same number of hydrogen, same number of carbon, same number of mass. But the environment of proton is different because of the different ring at different position. So the characterization plays a very important role. Right. So now, what is the interest of this chemistry? What we got it? What we develop. So now, see, the most important thing is that what I'm going to discuss here. Hydroemination of alkyne using DMSO D6. And DMSO D6, when we use, what we come to know that incorporation of deuterium in the molecule. So how it is coming? This is how. DMSO D6 with a base releases a D positive. Potassium tertiary butoxide releases this H, D, and D comes here. And again, you know, we have this tertiary butanol, N-heterocycle with potassium tertiary butanol, potassium tertiary butoxide. They will release this H, and this potassium tertiary butoxide will take this H, it forms tertiary butanol. And once you have this, after abstraction of this, and this DMSO will get incorporation of H, and what is happening? DMSO D is replaced by the H of NH. and it releases the D positive in the solution, which is responsible for giving D into the molecule. So we come to know about something new chemistry like DMSO D6 can be used as a deuteration source for organic molecule. So you can see here this, we got this, and once we have an electron rich system and D positive is there, you can get the incorporation D at these two positions also, right? So this is how we got this incorporation of this D. And then you can see hydroamination. We got the D here on vinylic positions. And once you have any alkyne having an electron rich ring, that can also be deuterated, right? So with this, something new chemistry has come out, and that we have extended, and we filed the patent, and patent have been granted. This is in commercialization scale. So this is the most valuable outcome of the chemistry, right? So small heterocycles you can deuterate. Toluene. So this toluene D3 is used as an NMR solvent, and sigma LH, it is 5 gram is nearly $500. And what we have done, simply this, using this toluene, you can make this, all the H can be replaced, not aromatic, only toluene 3, this H can be replaced by D. So you can make a deuterated toluene directly by using this chemistry. Metaxylene, orthoxylene, 1,3,5-trimethyl, so methylene, right? And styrene, methyl styrene can be deuterated. So drug molecule can be deuterated with this. So what is the best outcome is this. When you use DMSO D6, it can be used as a deuterium source. And when you look any literature, you will see the deuterium compound are so expensive. And this method is 15-fold lesser than what is reported. So like this one, you can divide 15 times, much cheaper. So by using this, when we done this chemistry, then we got invitation for account of chemical research. This is a very high reputed journal which invites the people who have made a significant contribution in that field. So because of the hydroemission chemistry, we got this invitation in 2016, and 2017 we published. Now you can see all these papers, they are all in hydroemission chemistry. Some more are there. I have not included here. There's up to 21. So second chemistry, again, is simple and most useful. So what we have designed, instead of halide, we replace with aldehyde. So what we thought, this amine will make imine first, and then this nucleophile can attack because imine is activated. So nucleophile can attack here, and this nitrogen will attack here. So there are two possibilities. Maybe first we can have an attack of this one, right? And or maybe first the nitrogen can attack here, so we can get ring B here. But both eventually will give the final product. It's the same, this one. So by using this, we have published more than 40 papers using the same chemistry. You can see here. Some of them I have mentioned here. What I mean to say, you need to think a basic chemistry. Once you think a basic chemistry and you can apply, you can connect, you can perform the experiment, you will get the good paper. But you need to make your efforts. Without efforts, nothing will come out. So see here, one bullet, more than 100 targets. So with using this chemistry, more than 100 scaffolds, we have successfully synthesized. And it's very simple, like orthoalkynylaldehyde, you can change amine building block. So these can be vary and these can be vary. So you can change the combination, and with the R group, you can have a variation R here, right? And nitrogen here, and quinoline here, indole ring here, thiophene ring here. So wide variety of scaffold can be constructed amine. And second is amine. So now look here. These are several papers using this chemistry. Now look here, what is the simplicity? In the beginning, we have started with this, and diphenylamine, very cheap, easily available in the lab, and silver and iodine is well known to activate this alkyne, any metal, right? So that metal you need to screen when you do the reaction. So how this? First is a imine formation, then attack of this, and then this. So one step, you got these fused benzimidazoles. Look here, all different scaffold. You will find all different, and R is variation can be done easily. So a very large number of scaffold can be synthesized, right? What I mean to say, I'm just showing you how easily the chemistry established can be utilized. Then next, what we have utilized, this amine with a pyrrole ring as a nucleophile, right? So first, what will happen? Imine, then in situ pyrrole, being electron rich in nature, will attack here, and you will get a quinoxylene. Earlier we got this benzimidazoles, fused benzimidazoles. Now here quinoxylenes, in wide variety of this you can synthesize. And then to confirm which is first. So you can see here with the time dependent reaction, we isolated the intermediate and we check the crystal, we develop the crystal, and then we come to know this is what is the first is forming, and then this one. So that also confirms the route, how the reaction is going, which is the first attack. And then quinoxylene ring also, we got this one. So first is this ring, right? Is this ring, and then attack of this. And then again, same chemistry, but smart thinking. And now benzoxazine, oxazine, isoquinoline, naphthalidines, all can be done. All can be made simply in water. What is change here is this substrate and this substrate. You can do the variation. Chemistry is same. First is a formation of this imine, right? And then imine will attack here, and you can get this one. And look here, all these scaffolds you can synthesize one, this, all different scaffold. Only the smart thinking is required with a commitment and with lot of efforts. And then this is a 3-component reactions, and that all of you know is enamine chemistry. So enamine chemistry, because we are using aldehyde. So what we thought, we can take amine, aldehyde, and ketones. So ketones, amines, and starting aldehyde is there, right? So first it will form an imine, right? And proline is used. So proline is a secondary amine. All of you know the proline secondary amine with ketone forms an enamine. So ketone and proline will react and they will form an enamine. And enamine will attack on imine, and this will attack here. This is how you can synthesize such kind of useful molecules. And all these wide variety of scaffold we have synthesized by using this 3-component reaction. And what is the mechanism? Now look here, it is a dual activation of electrophile and nucleophile. So this is a proline. Proline with a ketone will form in amine. Simultaneously, what will happen? You have aldehyde, amine, it will form imine, right? So now this is a ready to be attacked by nucleophile. This is nucleophile, this is electrophile. So what will happen? This, now you can see here, we have shown two things. Now here, this nitrogen lone pair will attack here. So one can get this ring, and this is iminium, and iminium is there, and this will attack here. This, right? So once this will attack here, what we will get? This F, and also this can go through path B also. This can directly attack here, and then it can attack here. So you can get F. I have shown two routes because here we did not isolate an intermediate. That's why both the possibility I have shown here. And then hydrolysis of imine, and that will give you this. So it is a smart use of the basic chemistry. And then we extended this chemistry with a amino acids. With a chiral compound, you can get a stereoselective compound, and that we have published in 2016. Right. And then look here, by using same chemistry, this we published earlier. Right. So these kind of compounds, this actually, if you look, this is a very, very useful, which is required for anti-HIV compound, anti-tumor compound. So, and this starting substrate can be easily made from orthoalkynyl aldehyde with a diisoester. Diisoester will give you this diketones, and diketones, you know, it's very reactive. And once you have a silver will activate this, and then this and this can attack here. And you can easily get such kind of molecule, which are very useful. This we have published in 2012. You can see here, wide variety of molecules. This, all we have made it. And further confirmed by the single crystal. Fine. And this is the mechanism which I have just described to all of you. Now, coming to the most recent one. Most recent one is, all of you know, Eza-Henry reaction. Actually, this idea came when I was taking classes for a natural product, where I was teaching for reserpine. And reserpine, they were making the indole by this Leames-Gruber synthesis. So in that, they have used the Henry reaction, right? So what I planned to replace this aldehyde with this and this through Eza-Henry. Eza-Henry, you know, this CS3 with a base. There is no catalyst, simply KOH demeso. KOH will pull out this H hydrogen, will generate anion, and anion will attack on this activated CN, right? And DMSO D6 is there. So C negative is there. It will take this proton D, so it will generate this. Now, what still we have this CH2 is highly acidic because of this electron withdrawing nature, will generate anion. So this anion is there, right? And here, what potassium is there? So potassium ion will also activate this. That we have performed through control experiment. When we use this 18 crown 6, 18 crown 6 is known to capture the K positive, right? When we use 18 crown 6, we did not obtain the product. So potassium is captured. That's why. So K activates this, and then it attacks here, right? And this is how later on aromatization, we can get NH2. And getting a NH2 in the ring directly is really challenging. And we have disclosed this thing. And again, you have NH2, NO2 also, that also can be reduced. And now once you have this NH2, lot chemistry can be done. Look, this chemistry, further we have extended. Now look here, these are so many useful natural product and this biologically important. So this, if you look this one, anti-tumor cytostatic active molecule. But directly NH2 is difficult. So we change this. Just now we made this. So what we thought, let's use this potassium tertiary butoxide. We successfully obtain this product. And how? Because you know this, because of this electron withdrawing nature, these hydrogens become acidic, right? So, and this is in resonance with this. So this can be easily formed. And once you have an anion, right? And this is Cn is active. So this will attack here. Once this attack here, now you can see here CH2 is there. Highly acidic hydrogen. So you got this NH2 here. Potassium tertiary butoxide is still present, right? So potassium tertiary, this is a, I have shown you ketone, this is a imine and active form, the CH2. So this will give anion that will attack here. And after that, still you have acidic hydrogen. With the release, you get NH2. And NH2 and Cn very close proximity. So this will attack here. And this is how you can get this product, right? So what I mean to say, what I have shown here in all this, some part of the chemistry which I started in the beginning, I continued, and up to the end, what I have shown here, at this paper we have submitted, maybe very soon this will publish. That's why I'm not showing each and everything. We have a crystal, everything, right? So what I mean to say, for your research, you need to design smartly. You need to design in such a way so that you can sustain not only one paper, so many more papers. Right. Now coming to the next part. How to get your research paper published in reputed journals. Right. So this is always challenging for all of us. But once you have a result and once see how to decide, there are following things. Identifying a target journal, following the journal's instruction, submitting the paper, understanding the decision process, revising a paper, answering the query, and reviewing proofs. These are the steps which are required when you have some result and how you can publish these results in top rated journal and good impact factor journal. Now look here, identifying a target journal. After preparing a manuscript, your next step is choose a journal for the publication of your research. And there are several criteria that should be considered in accurately selecting a journal for manuscript submission. When the paper writing is finished, means you got some result, right? You are looking like where to publish, right? When the paper writing is finished and the author consider the paper to be worth publishing, the next step is to submit it for publication, right? And where? So this is very important. The selective focus here is on journal article or conference paper. There are two kinds of, one is called letters of communication. Letters in communication always publish novel finding. An article is always a full paper where after having preliminary result that is published in letters of communication, after that you can continue that you can publish a full length paper. Although there's no restriction for having a novel paper, novel work you can publish in article. That's full length. That also you can do. But it is always there when you have some novel finding, something cutting edge, something different, which is not known, that you can publish as a communication or as a letter. Letter, they are having a short paper, 4-page length, something like that. But When you have a full length paper, there's no limit. You can have a 10, 15, 20, 30 pages, right? Like that. So you have to select based on your finding. And always there is a template for your writing a paper. So you need to choose a appropriate template, whether it is for article or whether it is for communication. It's all different. Communication is different, right? Article, it is different. So accordingly, you need to choose a template, and accordingly, you have to write the manuscript, title, abstract, introduction, result discussion, conclusion, acknowledgement, reference. All should be in proper order and as per the template, font size, and which letter, everything. So that according to that. So most important is your abstract and TOC. That should be eye-catching, right? Abstract are independent short text, generally not exceeding 10% of the paper length and or 250 words, right? So that should be a eye-catching. A good abstract should also generate curiosity or excitement among the audience by making the paper impression upon the target readers. Abstract might be more than plain description of their related paper content, right? Should have powerful statement enhancing the novelty of the research. Means that, see, when it goes for the reviewer first look your abstract, what is written, we do same like that. Just by looking the abstract and conclusion, we come to know whether it is acceptable or not, right? And now look here, this is one of our paper, is raw TOC, table of content, graphical. And see, nowadays journals, they look a perfect form of the paper. Now look this one, this is second one, is refined one. If you look first one, there are so many things here. NH2 group is there, right? But NH2 group is intact. But now if you have finding here, you can show this is primary imine is intact. So it is a chemoselective, regioselective, both. So you need to highlight your finding itself in your TOC as well as in abstract. So what is the conclusion of the paper? That should also be, conclusion is also very, very important. Unlike the abstract, the conclusion in the last part of the main body of paper or thesis, it is where a researcher actually answers the big question that impelled him or her to undertake the research project in the first place. Length and character, that should be, as per the general guideline. And language is also very, very important. The language should be a simple, because once your paper is published, it goes all over the world. It's not everywhere people are, they are good in English, Chinese, French. It's not like that. So you must write a paper in simple and very polite language. Cover letter is also very, very important. Once you write the cover letter, once you revise the cover letter. So your cover letter should, highlight editor's name, journal, right? Editor's name, name of the journal, and your manuscript title, article type, whether review is there or whatever is there, that you need to write. And submission date, and be background of study. So your letter is a very, very important, which you write to the editor. And when you write a revised cover letter, means once the paper came for the revision, you are writing, you need to reply each and every question raised by the referee, point by point. Point by point, you need to write the question 1, question 2, question 3 of referee 1, referee 2, right? So this need to be addressed properly. And match between the subject of your article and journal aim. it's also very important while choosing the journal, in which journal, whether it is related to your subject or not, right? So just look the aim and scope, and then accordingly you have to decide which journal is more appropriate. Second criteria, what is the readership and targeted audience? You have to look like which audience you are targeting. And so for that, what you can do, browse it through journal issue and check the countries and authors, institution affiliation for, right? So accordingly, you can decide the journal, which journal you need to choose. The next one is journal visibility. Which journal is more like visible everywhere and which is more circulating. Accordingly, you need to choose. I'll skip this. And checklist for the journal selection. Each and every journal, there is a checklist what need to be submitted along with the manuscript, that you should look it carefully, right? And each and everything you have to attach according to the checklist, right? So, and also you need to check like what is the minimum time that journal takes, so that you can look through the journals. Does the subject of your article matches with the journal? Does the journal accept the article type you intended to submit? Is the journal read by your target audience? Does the journal have an online edition? Online edition is always good because it goes widely everywhere. Is the journal impact factor in line with your requirement? Right? Is the journal regards as prestigious one of the field in your field, which is prestigious journal or not? How many times a year it journal published? What are the publication charges? Sometimes, there are very high publication charges. So if you don't have, then don't consider that journal. Consider something else. And then journal instruction that I have already, discussed with you. What category of article does the journal publish? What is the maximum length of article? What is the maximum length of abstract? So these are the questions which you should be ready before that. So what section should be article include? What are the guidelines for each? What guidelines should be followed regarding writing style? That is also important, right? And how many figures? Because some journals, they have a restriction of figure and tables. So that also you need to look at. And in what electronic format should the paper be prepared? So that should be looked at. And then submitting a paper is also very important. Earlier, it used to send through a mail. Just write everything, compile, and then send through the speed post, something like that. Electronic submission is very fast, right? Nowadays, most of them are electronic, right? So, and the most important thing, there are two things you remember. When you look at the editorial board, when you submit your manuscript, you can also select the editor accordingly. In some journal, they give the name of associate editors. So you can check, you can assign those editors, and then those editors will send your manuscript for the reviewer. And when the reviewers submit the comments, the editor-in-chief of that journal take the decision for whether it should be accepted or rejected. And most important, plagiarism check should be done before submitting the manuscript, right? And now in the last part, when your manuscript comes with a decision, you look it properly. And sometimes they reject, but in the rejection, they write something, so you can again address all those questions and you can again submit that paper along with all the answers or experiments suggested by the referee. And when it is sent for minor revision, major revision, should not take it lightly. Should not. You need to address each and every questions raised by the referee as well as editor. And in the cover letter, you need to describe everything in detail. And if required, you need to give a reference. If you don't have, some reference must be there for your proof or your answer, so that you need to give. And answer all the queries. Highlight the part you added in manuscript with a yellow color. Whatever changes you have made, it should be highlighted, so that once you send the revised manuscript, the editor should know what changes you have made. Once it is accepted, then finally it will come for the reviewing the proof. Sometimes proofs are not perfect. You need to check it very, very carefully, because they are editing, people are there, they edit your paper completely, and sometimes they do the mistakes. So you need to look each and every line very, very carefully. Right? So these are the some points. I was in very hurry at the end. I was very fast because due to time constraint. So these are the parameters which you need to consider when you write a manuscript. Or what in the beginning I described, that you need to look for establishing your lab. Whenever your first part, you start your lab, always there are challenges. But that in the beginning, once you cross that hurdle, you are one step ahead. You are on the track, right? So you need to do really hard work for first paper or first project. So these are, rewardees of our best papers. You can see Tripti, she in 2014, she, based on the publication, she got selected for the Lindor Nobel laureate meet. And chemistry terms comes after 3 years. All right, every year, sometime physics, sometime medicine, sometime chemistry. So chemistry terms comes 3 years. So it was in 2014, then 2017, one of again 2014 Tripti, and 2017 the Monica, and this is simply based on the publication, not else. And Rakesh, one of the best students from our lab. And all of you know the Jonathan Claydon, we all read the books. He did postdoc with Professor Jonathan Claydon, and also got a Marie Curie fellowship in 2019. A very prestigious. In a year, in every month, you will get more than 10 lakhs rupees as a fellowship. And the mentor also get the fellowship. Mentor also get the money for the research lab once you get the Marie Curie fellowship. And at present, he is working with in US, Urbana-Champaign. When he was in UK, he was cool, because UK there is no restriction. 5 o'clock, 6 o'clock, you can come back. But nowadays he is in US, where timings are up to 11 p.m. night. So before that, he cannot leave the lab. So morning 9 to 11, he should be there. But see, these are the things when you can learn. And now you can see NOS Best Thesis Award continuously 5 years. You can see 17, 18, 19, 20, 21. So this is, we have made the history. And 2014 she got, but after that I was not having any student with publication, so I did not nominate it. Actually, in between I forgot it. And now you can see we have made the history, and she got $1,500 when she in 2014 she got NOS Best Thesis Award. It is a very competitive. All people from ICERS, IIT, CSIR lab, university, they apply, nominate the student. And in the PhD thesis, those who are getting the best publication, only those get selected. So these are our star people and who made this lab in university. They made the university proud. And these are the contributors of my lab. And because of them only, I can say I am in front of you. And all of them, they are in some good places. Rakesh, he is in Chapman. And Kashi Shankar, he is drug inspector. Jaspal is in the US. Nagendra in South Korea. Ritu in Uttarakhand somewhere. She's Rupesh in KMC. Megha is in Abu Dhabi. Tripti is in Hindu. Rajiv Ranjan Jha, he's in some company and he's earning 35 or 40 lakhs per annum. And Abhinandan is also in company. Vinita and Satyaprakash both are in the US. Shivake Reddy is in Jubilant. Monica in Ramjas College. Rakesh now in US. Sonu, he's in Hansraj College. Deepak in Ayush. Shilpi in HPCL, this petrochemicals. And Pradeep, he is in IIT Kanpur. And Vinita, both are together. So this is what is my research group. And this is beautiful ground of our Department of Chemistry. I love it. And I enjoy the chemistry discussion with all my students in this like this in front of this is my lab, left hand side. So thanks everyone. Thank you. And I hope I could justify like how you can establish your lab, how you can design the chemistry. It is not any tough. The only you need to have efforts. You need to make your commitment. You need to work hard. Right? Then only you can get what you plan. And I am the example in front of all of you from the university system. The people say we cannot do, but we can do it. All these publications, you can see what I have done from this department, not from any other place, from this department. If I can do, others can do, you people can do it. But the thing is that you need to go to the right track. Right? So thank you all of you.
Thank you so much, sir. It was such a pleasure to hear you. I can't tell you. It was not just that it was informative, it was inspiring. And your journey as a researcher to become such an accomplished one, I mean, I'm totally inspired. I mean, I can't tell you. And I'm sure, like me, all the participants are just completely inspired and totally wanting to do this and continue with their research and probably start if they're just starting up. But so it was really nice. One, how you started, how you progressed through the research. I mean, although my organic is not so good and I've almost forgotten, but it was such a pleasure to hear you and your journey. I mean, it's totally, and not just ordinary research, it was inspiring research. Your students are doing so well. And I don't think
no, Malika, it's not like that. One need to be dedicated and committed. Nothing else. It's a simple thing is required. But it's true, very hard work is required.
A lot of hard work.
Out of 24 hours, 18 hours, I work for my lab.
I know, sir. I'm totally flabbergasted. I can't tell you. I'm so impressed. But sir, there is a lot of admiration for you on the YouTube also. And I can tell you that there are participants who are all gaga over you. So I can't tell you that. We'll share the screenshots with you. Anshika will do that.
Sure.
So can we take one or two questions from the audience?
Sure, sure, sure. Why not?
Yeah. So,
I'll
sir,
be happy.
so there is one question from a participant, whether click chemistry can be used in such preparation or library of compounds?
Yeah, sure. It is a well established.
Okay.
The click chemistry, sharpless. And they have already explored.
Okay.
Click chemistry is well explored, but still, if you can connect something different, always you can explore the click chemistry. Still, a lot of publications are coming on the click chemistry.
Right, sir. Right,
Right.
sir.
In the click chemistry, there's always, you have to look the regio selectivity. Right. Because there are two possibilities for making a triazole in that.
Okay. So I do know a little, but maybe thodi organic.
No. See, any of you, those who are listening my lecture, if you have any query, you can always write to me, or if you are in Delhi, you can come and discuss with me. I am always there for the students and teachers, those who need help.
That will be my pleasure. So I'll definitely explore and come to you. So there's one more question.
Yes, go ahead.
Can we know about one-pot reaction in heterocyclic chemistry?
Yeah, see, there are so many things which you can do one pot, right? Like that is called a sequential reaction or three-component reaction. I have shown you here, right? So in water that we have done is a one-pot reaction. Like first is, see, in the beginning, what I have shown all are one-pot reactions. Because once you get an imine, then second nucleophile is there that will attack, and you will get another carbon on carbon nitrogen bond formation that will give you the product, right? So this is all called a three-component reaction or one-pot reaction.
Right.
All three components you mix together, that I discussed with the enamine chemistry, right?
I saw
enamine chemistry, you have this orthoalkanylaldehyde and you have a amine, so they forms imine. Simultaneously, what another you have proline and any ketone, so they forms enamine. So enamine and imine means one. See, what is required, you have to design in such a way, so one side you generate a positive, another side negative, so you have a possibility of making a bond. Chemistry is nothing, just you need to design such a way so that you can have a positive and negative center where the bond possibility is there.
Yes, so that's a very simple way of explaining the reaction.
Yes, it's just a very simple thing. This is how I use this chemistry.
So that's very nice.
And always remember, when you are teaching, right? And once you are discussing the book or something, you always get some ideas and connect those ideas with your research. I always enjoy, when I'm teaching this natural product. Nobody was taking that course, but now I'm enjoying that natural product.
Yes, sir.
And get so many ideas in that. And last part I have shown you, right?
Yes, sir. Absolutely.
Henry reaction is simply, what is Henry reaction? If you have any aldehyde, you react with nitromethane with the base, you will get double bond. But instead of aldehyde, I change cyano because cyano is equivalent to the carbonyl group, right? So in that case, you will get amine with a carbon. Enamine you will get. So enamine you can utilize. So this is the chemistry I have designed and I've used.
That's very nice, sir. And so we're going to call you for a talk for the students. At least they will understand that complicated reactions can be understood in such simpler manner.
Yes.
Yeah. So there's one more question, and that's the last one that I will take.
No, go ahead.
What is the difference between a paid journal and an open access journal?
See, okay, that's a very good question. There are two things. Paid journal, there are some predatory journals, right? And they simply publish whatever you send, they will publish it, right? And they ask some money. This is the business nowadays started. And a lot of people, they are doing just paying some money and getting their work published. Actually, these predatory journal, they don't send for the review. Their own people are there. They just accept it. Because from these kind of journals, you won't get a nice comment, a good comment. But there are open access journals. Like ACS Omega is there. So many others are there. They take the charges, right? And they can waive also. See, everybody should remember, when you fight, you will get the waiver. When you say you are from the developing country, you don't have money, your lab is this and that, and we don't have money. I do like this. Open access journal are those journals, right? Once you are paid, it is open all over the world. But like in Delhi University, some journals you can see through online. But for that, our university is paying. Those are not open access journal. But open access journal you can open from anywhere. There's no subscription is there. And because of that, they get more readership. Like RSC Advances is there. It is open access journal, but they charge. They charge for open access journal. But I would suggest there are so many reputed journal, right, which goes all over the world, all ACS publications. Now everywhere they started some business.
Yes.
Some of them, they are paid. And they are paid and open access. You have to pay, then it will be open access. They always ask whether you want to open access or not. So if you are interested, you can pay and ask them for the open access.
Yes.
Because you will get more citation when you have an open access journal.
Yes, people will read more.
Yeah.
Yes.
Because some people who don't have access, they will also get when it's open access. If it is not open access, you need to have a link or subscription should be there.
Right.
Like in university, Delhi University, we have subscription through Infinite, through UGC, right? They subscribe all. But right now, some journals are not opening. Because that yearly, it ends. Every year, it need to be revised, renewed.
Right. So, sir, that's all. I think I'll take these many questions. So, sir, I'd like to thank you. On behalf of the Miranda House and the Ramanujan College, I would like to express my gratitude to you, sir. You were just wonderful. I mean, I can't express how good you were.
No, I really enjoyed. For this, up to 2:30, I was doing some slides and something like that.
But it was such a pleasure. Thank you for sparing your valuable time.
I cut down in the last part.
No, but sir,
I wanted to continue more, but it will be difficult for all these, so sir, I made it short.
Sir, I'm sure Ramanujan College is going to invite you now for the research methodology workshop that they are planning. And Anshika is going to do that because we would like to hear about these paid journal, open access journals a lot. So it was thank you so much, sir. So thank you for sparing your valuable time and sharing your immense knowledge with all of us. And last but not the least, I would like to thank our audience, our participants who have spared their valuable time from the weekend to listen to us and to listen to what valuable information sir could share.
Most of these are from Delhi University or some other places also?
Pan India, across India, people have joined from chemistry departments and they're all listening to you, sir, live right now.
Okay. Thanks, everyone. Thank you.
Thank you so much. So, well, ladies and gentlemen, I'll wind up the session. Thank you so much.
And thank you. Thank you
so much, sir.
Malika ma'am, you can stop